Welcome back to part 2 of DC and AC analysis for BJT. In this video, we are now going to try to solve a sample problem. We are going to conduct both DC and AC analysis. So for the DC analysis, you get this circuit. If you don't know how to come up with this circuit, watch my previous video on explaining the preparations for DC and AC analysis. Now in DC analysis, you can solve for the three currents, the base, collector, and emitter currents, the VCE, the VBE, the VC, VB, and VE. So let's solve for those. Looking at this circuit, I'm gonna start from the left side. And if this is not familiar to you, you should watch another video of mine explaining how to use the KVL or the Kirchhoff voltage law in order to get the equation. So now let's visit our bag of formulas and select the one for the left side. VCC is equal to VRB plus VBE plus VRE. As you can observe, there is no resistor in the emitter side, which means there is no VRE. So we erase VRE. What's left is VCC equals VRB plus VBE. From Ohm's law, V is equal to IR. So let's change this VRB into IBRB. Now we substitute the values. VCC is equal to 8 volts, IB is missing, RB is equal to 560k ohms, and VBE is always 0.7 volts. Solving for IB, we get 13.0357 microamps. Now let's open up our bag of formulas again to see what other parameters we can get from just IB. Let's use IC is equal to beta IB to get IC. Just simply plug in the values and IC is equal to 1.29054 milliamps. Now we have to find the last current, IE. Now we can use the first formula or we can use the third formula. Let's just use the third formula. IE equals beta plus 1 IB. Just plug in the values and IE is equal to 1.30357 milliamps. And of course, we know that VB is equal to 0.7 volts. VBE is composed of VB and VE. Now, since we know that VE is non-existent, we can simplify this formula into VBE is equal to VB. Therefore, VB is also 0.7. In the same way, VCE is also equal to VC because VE is non-existent. But we don't know the value of VCE. So let's go back to our figure and figure it out. Now let's look at the right side because the VCE is located in the right part. Let's open up our bag of formulas and we'll use the formula for the right side. VCC is equal to VRC plus VCE plus VRE. Again, VRE is 0, so we're left with VCC equals VRC plus VCE. Using Ohm's law again, V equals IR, we can replace VRC with ICRC. VCC is equal to 8 volts. We solved IC earlier and RC is equal to 1K. So solving for VCE, VCE is equal to 6.70946 volts. VC is also the same. So we have finished DC analysis. We have solved for all of these parameters. Now let's proceed to the AC analysis. For the AC analysis, we come up with this figure. If you don't know how to make this figure, go back to my previous video where I explained DC and AC analysis preparations. So let's start by solving for RE. This is a new formula. RE is equal to 26 millivolts over IE. Let's add that to our bag of formulas. Now substitute IE that we solved before. Solve for RE and RE is equal to 19.945205 ohms. Now let's divide this circuit in half, right about here. This division divides the input side from the output side. We're gonna focus first on the input side. The Zn is the sum of all the impedances on this green side. So in order to find Zn, we need to simplify this circuit first. Let's start with this side here, the base area of the transistor. You need to solve for the total impedance in this base area. Let's call it ZB. We use Ohm's law, V equals IZ, in order to solve ZB. ZB is equal to VB over IB. We already solved IB earlier. Now we have to figure out what is VB, or the base voltage. VB is the sum of all the voltage drops in this area. In this case, we only have one voltage drop because there is only one resistor, and that is the beta RE resistor. So to find VB, we use Ohm's law again. V equals IR. Looking at beta RE, the current that passes through it is IB. So therefore, we can substitute VB with IB beta RE. The two IBs cancel out, and we're left with ZB is equal to beta RE. Plug in all the necessary values, and then we get ZB is equal to 1974.575342 ohms. Now, let's take a look at this area here. Let's call this ZI. In order to solve for ZI, let's simplify the circuit like this. We already solved that part, so let's just simplify it as ZB. Now, this circuit right here is just a simple parallel circuit. Therefore, ZI is equal to 560 kiloohms parallel to ZB. Substitute the necessary values, and we get ZI is equal to 1967.637 ohms. Now, we're finally ready to solve for this big area here called Zin. Let's also simplify this circuit even more. We know already that this part here can be simplified as ZI. And now, it forms a simple series circuit. So, it's just a simple addition. Zin is equal to 680 ohms plus ZI, which leads to Zin is equal to 2647.63739 ohms. Now, let's proceed to the right side, or the output side. Let's find the Z out. In this case, it's just a simple parallel circuit of the RC and the RL. So it's just simply Z out is equal to 1K parallel to 1.2K, which means Z out is equal to 545.455 ohms. We are almost there. Now let's find the AVS, or the voltage gain in terms of the source. There are a couple of things we need to find first. We have to find VO, or the output voltage. We have to find VI, or the input voltage. And we need to make use of this formula, which is a voltage divider formula. Let's add this in our bag of formulas. Now we find the VO. Using Ohm's law, V equals IZ, the output voltage is equal to the output current times the output impedance. If you look here, the I.O. is just the opposite of IC. Therefore, I.O. is equal to negative IC. Let's leave that formula for now and proceed to VI, or the input voltage. The input voltage is the voltage across this resistor or across this resistor. Let's choose to solve this resistor because its current and resistance is already given. Using the Ohm's law, VI is equal to the current IB times the resistance beta RE. Now let's divide VO and VI together. VO over VI is equal to negative IC Z out over IB beta RE. IB times beta is equal to IC. So let's simplify it so we can cancel both ICs. We are now left with negative Z out over RE. This is actually the formula for the voltage gain, but not in terms of the source. Plug in the values, and we get VO over VI equals negative 27.348. Now let's get that formula from our bag of formulas. VI is equal to VS times ZI over ZI plus RS. Modifying, we get VI over VS is equal to ZI over ZI plus RS. Plug in the necessary values, and you get VI over VS is equal to 0.74317. Now, why did we do all this? Because if we multiply VO over VI and VI over VS, the VI's will cancel, and you're left with VO over VS, which is exactly the formula for the voltage gain in terms of the source. So we just multiply their values and we get negative 20.32414. Now let's proceed to AIS, or the current gain in terms of the source. The formula is the same as voltage gain, output current divided by the source current. To get these currents, we have to use the Ohm's law. The output current, as shown in red, is equal to negative VO over RL. It is negative because the current is going away from the resistor. The source current is shown in green, Vs over Z in. It is positive because the current is going towards the resistor. Now we rearrange the values, and the result is negative VO over Vs times Z in over RL. VO over Vs is the formula for AVS, so we can simplify this further. Substitute all the necessary values and you will get AIS is equal to 44.8419. That's all for today. If you want me to answer another problem, just comment down below and stay tuned for more videos like this.